When we try to discuss the constitutive models for single crystal, so we have the idea that Schmidt law predicts the plastic and perfectly plastic behavior of a crystal. So here actually define the yielding occurs over a slip plane in one specific slip direction, and it corresponds to a specific slip system for the different crystals, and at the same time there may be the possibility of the several slip systems may active at a time. But purposefully, when you try to analyze the plastic deformation of the single crystal structure, we generally focus on the plastic deformation behavior on single slip system. So here yields begins, or we consider there is a yielding starts when specifically it overcomes the critically resolved shear stress for a specific slip system of a crystal structure. So, but this critically resolved shear stress is independent of the shear stress value or any other normal stress on the lattice plane. In fact, this mechanism, when you try to explain the slip for a specific crystals of a single crystal structure, so there is a transition from the elastic to and plastic zone. It's not not in a smooth way. So it can also be possible to explain the transition, smooth transition from elastic to plastic deformation, and that can be better explained by the power law behavior. And we have observed that when you try to explain the plastic deformation in continuum plasticity mechanics, in that case, so we describe the deformation of the material in terms of the plastic deformation material using the power law relation. So that actually represents that normally the complete plastic deformation zone by neglecting the elastic deformation component. So that is a typical type of correlation between the stress and strain that follow the power law relation can be explained for the smooth transition from the elastic to plastic behavior. Another significant point here, when you try to analyze the deformation behavior, probably the rate of the strain is more important on the slip system, and that can be explained by the constitutive relations. So by assuming the kinetics of plastic flow, which is rate sensitive, we can avoid the non-uniqueness of the set of active slip system, and that is typically present in the rate insensitive model. So there is a significant things, two things. One is that whether there is a deformation which is rate sensitive or whether deformation is a rate insensitive. That typically we explain in plastic deformation over a continuum scale. We express the relation between stress and strain either by strain hardening coefficient n sigma equal to k epsilon to the power n, or if there is a strain rate sensitivity index, if we consider, then we explain the relation between the strain, stress and strain rate. So similar kind of philosophy can be used here to explain the plastic deformation of the single crystal structure. Let us see how the plastic deformation happens. So once there is a so many slip systems is active at a time, so that questions of the crystal reorientation actually comes into the picture. But why do slip system reorient and why the crystal lattice rotates? We try to understand these two phenomena here, but if we just focus on the figure, here see the crystal slip system here, and so many slip system, it may or probably it is representing in the, there are several parallel planes, and if there is a axial stress value and at the on the axis initially, and the deformation behavior maybe looks like this. So there is a, with respect to one plane of the atoms, or maybe with respect to several planes, there is some relative displacement between them, and this kind of displacement specifically for the single crystal structure, we can found out that if there is no geometrically constant condition, then single crystal deformation or single crystal behaves like this and over a several slip planes. And of course, there is a angle x0 is the angle between the slip direction and the normal tensile axis. Now, if it is possible to put the constant, that is actually happens in the practically, because it is the slip planes acting in such a way, and if you put the constant here, then continued axial alignment of the crystals looks like the third figure here. And here if you see, when you try to make the constant deformation or try to make the slip behavior over a geometrical constant is there, then to arrange that slip planes, it is subjected to that some kind of bending as well as the rotation. So that means the slip planes and slip direction in a crystal are finite in number and fixed to the lattice point, but an arbitrary motion can be accommodated in general by allowing the crystal lattice to rotate, and that can be better explained if there is any geometrically constant is there or not. If there is a geometrically constant, then definitely the crystal planes is subject to some amount of the rotations. And with respect to the each and every slip plane, when there is a sequentially active the different slip plane, with respect to one slip plane to another, they will try to reorient with respect to each other. So this is the philosophy of the plastic deformation for a single crystal structure when there is a several slip planes active. Now, how to form the constitutive models for a single crystal structure? So here the target is to analyze the constitutive model what we have explained specifically in the continuum plasticity models. So here similar kind of things we can explain in such a way that plastic flow in a single crystal is anisotropic, so cannot be modeled using the simple constitutive equation. So this plastic anisotropic behavior, it's very difficult to or not easy straightforward to model, because in this case more complicated constitutive law can be used which consider the slip activity in the crystal directly. Let us see what we can accommodate or we can explain this constitutive model or to develop this constitutive model in case of the single crystal structure. The main application of the constitutive equation is to model the rotations of individual grains in a polycrystals, and hence to predict the evolution of the structure and to account for the effects of structure on the development of anisotropy in the solid. So main reason for the anisotropy in the crystal structure, that actually comes from the structure formation. So if you try to incorporate the effect of the structure, probably in that case we can include the effect of the anisotropy in a plasticity model of the single crystal structure. Let us look into that example. For a special orientation of the tensile axis, more than one slip system may be activated. That we have already explained that at least in the ideal condition at least 5 slip system will be active to maintain the compatibility condition in a deformation of a single crystal structure. So for example, if an FCC crystal is loaded parallel to 1, 0, 0 direction, that is any one of the axis of a unit cell, 8 slip systems are subjected to the same amount of the resolved shear stress and so are active at the same time. So this is just a typical example that several slip systems may active depending upon that which direction the load is acting. In a tensile test oriented for single slip, the crystal rotates so as to align the slip direction with the loading axis. So if the tensile test oriented according to a single slip, then crystal also rotates to align the slip directions according to the loading axis. At the same time, the crystal rotates for enough to activate a second slip system. The exact point where this occurs depend how the crystal actually becomes harder, or how the crystal hardens. The rotation direction changes after the second slip system becomes active, and eventually the loading axis aligns with some specific direction. This can be a stable orientation and the crystal continues to deform in double slip without further rotation. So, actually all these points signify that with the application of the load, how the slip plane actually reorient with respect to first slip plane and the second slip plane, and how they can configure in such a way that it is accommodated by amount of the rotation. So, by taking into all this fact, probably it is better to explain that how the models can work. Now, for a single slip, if we consider the single slip system, apply the minimum work principle, probably we can derive this sigma by normal stress by shear stress in this case is equal to, in terms of the rate of strain, shear strain rate and the normal strain rate ratio, and that is represented by 1 by m, and m is basically here cos phi, cos lambda, that is the direction cosines with respect to the defined axis in the crystal system, that we have already derived. And here we can find out that sigma equal to stress equal to shear stress by m. Probably m we can consider the resolve. This is the one factor that depends on the orientation of the axis with this slip direction normal to the slip plane and the tensile axis. So, if we compare that, already you have defined that if you polycrystal is subjected to some amount of the deformation and random orientation of the crystal, in that case the Taylor factor for orientation dependence simply estimated by this way. So, that Taylor factor is basically ratio of the incremental shear strain in terms of the with respect to the incremental normal stress, and that is the ratio sigma x by tau, that is normal stress by shear stress. That is the typical way we estimate the Taylor factor to link between the normal stress and the shear stress component, or to link between the increment of the normal strain to the shear strain. And of course, this factor takes into effect the orientation dependence. And while looking into that similar thing, we can find out that probably that in this case the shear stress is the shear stress describe the dependence of the critically resolved shear stress on a strain, that means specifically on the slip curve, based on the idea that the critically resolved shear stress increases with increasing strain. So, therefore, m can be the maximum, Schmidt factor m can be the maximum when both the angles become 45 degrees. That means m, the maximum values of m can be 0.5 here. Now, this shear strain component can also be explicitly as a function of the ratio of normal strain by m. So, here if we see that from the factor of this Taylor factor, so here probably we can represent that from here, that shear strain is basically the shear stress into shear stress equal to normal strain into m, or shear strain equal to norm m equal to here basically 1 by m. Now, if the finite strain is imposed, the shear strain increment is given by the macroscopic strain divided by the Schmidt factor. So, probably that macroscopic strain can be represented by the Schmidt factor, where Schmidt factor m actually represents the cos phi cos lambda. Now, after each increment, the Schmidt factor must be recalculated because the lattice orientation has changed in with respect to the tensile stress axis. So, here the point, if you try to correlate with the continuum plasticity model, where also we have discussed that in the plasticity analysis we generally provide in terms of the incremental mode, basically the incremental mode in the sense the incremental amount of the strain component and what is the corresponding and link it corresponding stress value. So, similar philosophy can also be used here, where the incremental shear strain is basically incremental normal strain by m. So, and each time we recalculate the m factor m because the orientation actually change with respect to slip plane or with respect to the tensile stress axis. So, once we recalculate all these things and we can accumulate the total amount of the strain and we can use the correlation to link between the stress and strain in terms stress strain or whether it is normal stress or whether it is shear stress component. Now, we will try to focus on the plastic versus plastic deformation for the analysis of the plastic deformation of the single crystal structure. Selection of the slip system for rigid plastic models, that means rigid plastic models means that the plastic deformation we just analyzing the deformation of the plastic part without the effect of the plastic component. Assumptions for fully plastic deformation, the elastic deformation rate is usually small when compared to the plastic deformation rate and that can be neglected. That means in case of rigid plastic models probably we can neglect the effect of the plastic component. But the elastic strain is limited to the ratio of the stress to the Young's elastic modulus. But perfect plastic material is where the equivalent stress is basically with respect to the initial yield stress. But for most of the metals, the initial yield stress actually 2 to 4 times of magnitude less than that of the elastic modulus, so that we follow that ratio is very small as compared to 1. So, once the elastic deformation rate is considered, it is reasonable to model the material behavior using the rigid plastic model. The plastic strain rate is given by the sum of the slipping rates multiplied by the Schmidt's tensor. So, it is basically that first thing is that when you try to focus on the rigid plastic models, probably we can neglect the elastic component, but till we can estimate the rate of elastic deformation and we can compare with the plastic deformation. So, probably in this case the rate of elastic deformation is very small as compared to the plastic, so that we maintain the ratio which is very low, very much less than that of 1. But when you try to estimate the amount of the total plastic increment of total plastic strain, in this case probably we can sum it up what is happening for over the different slip system, and that accordingly we can estimate the rate by looking into that what is the Schmidt factor for all these cases. Now, here also we can implement the von Mises yield criteria in the plasticity model. The number of possible active slip systems probably in cubic metals is greater than the number of independent components of the tensor strain rate, that is represented by dP from the mathematical point of view. That any combination of the 5 slip systems that satisfy the incompressibility condition can allow the prescribed deformation to take place. So, that we have discussed the what is the requirement of the at least 5 slip systems is active at a time, so that it can maintain the incompressibility condition. The requirement that at least 5 independent slip systems are required for plastic deformation is known as von Mises criteria here. But if less than 5 independent slip systems are available, the ductility is predicted to be low in the material. The reason is that each grain will not be able to deform with the body and gaps will open up, that means it will crack. So basically the compatibility condition is the main issue. Based on that, we can decide that at least 5 independent slip systems can be active at a time. If it is less than 5 independent slip systems are available, probably the ductility predicted to be very low in that material, because in this prediction, if it is less than 3, it will violate the compatibility condition. That actually creates the crack formation during the deformation. Now, we will try to look into that hardening rule in case of the crystal plasticity model. So, here the resistance of each slip plane to shearing increases with plastic deformation, and that is the effect of the due to strain hardening effect. Our typical stress strain curve for a single crystal structure we have already discussed, and we observed that at stage 3 the deformation, at the large strain the hardening rate actually decreases, and that happens due to the dynamic recovery. So these are the typical observation from deformation stress curve in case of single crystal structure. Now, how to use the hardening rule in case of single crystal plasticity model. So first thing is that we consider the shearing on the alpha system increases its own strength, probably that is defined by G alpha, and this is known as self hardening. Self hardening in the sense the increment of the strength level due to a specified slip system or due to a specified shearing operation on a slip system, but at the same time this slip system can also affect the deformation behavior of the other slip system. So that means in the second case the shearing on the one specified slip system, alpha slip system, also increases the strength of the all other slip systems, and that is represented by G beta. So therefore, but beta not equal to alpha, and this type of hardening is known as the latent hardening. Therefore, self hardening can be measured using single slip test, but latent hardening is often measured by the first deforming the material into single slip, then reloading the specimen to activate the other slip systems, or maybe to activate the second slip system. So these are the way to measure the hardening effect, whether it is self hardening or whether we can measure the latent hardening. So basically the self hardening, the increment of the stress level and strength level in the or for a specific slip systems, direct effect on that, or secondly the increment of the strength level for a specific slip system that will affect the other slip system for a specific deformation behavior of a single crystal structure. So once we can measure the self hardening and latent hardening, probably we can use to form some equations to predict the hardening behavior of a single crystal structure. So latent hardening is often quantified by the latent hardening ratio, which specify the ratio of the strength of the second system to that of the first system. So latent hardening ratio R can be defined the strength of the second system, strength of the first system. So this ratio we can use it, but it's not necessary for the several slip system. Always the ratio should be maintained as a constant. So therefore the details of the hardening behavior of single crystal structure, in general it is very complex in nature. So this was just to idea that probably we can use the hardening like continuum plasticity model for a single crystal structure also. Now when you As a part of the crystal plasticity theory, the constitutive equation must specify the relationship between the stress measures and actually deformation measures. So, in particular, the constitutive equation must relate the elastic part of the deformation gradient to the stress and the rate of the shearing on each slip system to the resolved shear stress. So, specifically here we are trying to focus on the rate of shearing on each slip system and what is the corresponding to the resolved shear stress. So, this constitutive equation will always try to affect or these two facts, the elastic component as well as the rate dependency of the hardening effect. But if we see the elastic stress relation in the crystal plasticity, we have already explained the elasticity in the single crystal structure. The relation between the stress and the elastic part of the deformation gradient actually follow to procedure developed for finite strain plasticity. So, that theory we have explained. And now plastic stress and relation in crystal plasticity, here it is more significant because the plastic constitutive equation specify the relationship between the stress on the crystal and the slip rate on the slip system. So, stress and the slip rate on the slip system, the crystal plasticity try to correlate these two quantities. Therefore, most sophisticated equations are required to accurately describe the latent hardening behavior in this case to probably model the crystal plasticity or single crystal structure. Now, in single crystal structure, the flow rule can be decided like that. Consider the viscoplastic flow to predict the slip rates in a single crystal structure. So, probably we consider the viscoplastic behavior of the material to predict the slip rates in a single crystal structure. So, always we try to focus on the slip rate dependent, that avoid having to use an iterative procedure to identify the active slip system. So, probably it is difficult to track the individual slip system in terms of the single strain rather than strain rate. So, when you try to consider the capture the rate of the slip rates or maybe in terms of the strain rate, it is more representable than only on the deformation behavior in terms of only single strain component. So, this is one of the simplest flow rule generally used, and we see in terms of the rate, and probably this rate is significant because we have considered the flow of the material as a viscoplastic flow. So, for this viscoplastic flow of the material, we can use this relation. So, where tau actually is the resolved shear stress on the slip system, G is the current strength which evolves with the plastic straining, and gamma 0 dot actually represent an M at the material property. So, M is not the Schmidt factor here, probably it is the other properties of the material constants and depends on the properties of the material. So, these are the typical flow rule probably we can use in the crystal plasticity model. Now, if it is more going into the crystal plasticity model, the hardening rule probably must specify the relationship between the slip system strength and the plastic strength. That also it is obvious, the system strength to the plastic strength should be correlated, and that is the better represented by the hardening rule. So, at time t equal to 0, probably each slip system has the same initial strength G0 if we assume that. Therefore, the slip system increases in strength as a result of the plastic shearing according to this equation. So, here you see the H alpha beta are the strain dependent hardening rates, and the hardening rate is approximated by this curve H equal to R alpha beta, and where H is a function of the total accumulated slip on all slip system. So, gamma bar is actually the total accumulated slip for the on slip system, and here the hardening rate is approximated this. So, basically the hardening ratio and the functional form of this curve, hardening curve, with respect to the total accumulated slip on the all slip system. So there may be the several possibility of represents this hardening, this curve, the hardening rate curve, this several functional form depending upon the deformation behavior of the crystal structure, or several postulated theories are also there. So we can use accordingly this hardening rate curve, and we can use the it in the to predict the hardening behavior of the single crystal deformation. Therefore, the plastic properties of single crystal structure actually strongly sensitive to the material crystal structure as well as the composition. So it is very much dependent on the crystal structure and the composition. So accordingly, we can derive the different types of the curve that represents the relation that actually represents the rate of hardening. So I am not going into that details on how we can do that, but rather we can focus on the very basic idea how we can use it. Now we come to that polycrystal plasticity theory. So basic idea on that, the theory actually built on the physics of the single crystal plastic deformation behavior, and always we try to represent the relation between the macroscopic to the microscopic quantities in terms of the stress and strain. That is the basic philosophy of the polycrystal plasticity theory, and in this case the mean field hypothesis is probably more appropriate. So that normally we represent the polycrystalline theory is the averaging behavior of a single crystal structure. Now here need for a mean field hypothesis to build the theory. So at the continuum point probably represents the aggregate behavior, and we represent the stress component as the average of the individual component, and if you see that is the link, an individual crystal probably having the stress component sigma c, and when we averaging by the several crystals, and we can find out this is the average value, and that is true for the polycrystalline structure. And there are several field theories are also there, and using that field theory probably we can link from the single crystal behavior to the polycrystalline plasticity theory. Now one of the polycrystalline plasticity theory is the Taylor model, and that actually decides the upper, sometimes it is called the upper bound theory. So in this case what happens, but before looking into that, let us look into the right hand side figure. Here if we see there is a structure, and probably there is a fiber structure, and if we see that if we apply some kind of load, maybe compressive load with the specified direction mentioned in this figure, it actually creates the condition of the isostrain. That means same amount of the deformation, even there are the two different components or two different materials are there, and that condition says that total deformation or maybe total strain remains the same if we consider the individual material, and this is the condition of the isostrain. But this stress or maybe applied load will be shared by the two different materials. It actually depends on the orientation of that materials. So here suppose one is the stress will be divided into two components, sigma x and the sigma d. That stress is actually applied to the two different individual components of this material. Now by looking into this concept, we will try to explain the Taylor model, to what says that all single crystal grains within the aggregate experience the same state of deformation. That means same amount of the strain, but equilibrium condition across the grain boundaries violated because the stress states required to activate multiple slips in each grain vary from grain to grain. So in case of polycrystal, if you try to correlate these things in the polycrystal in a polycrystal sample, so in this case actually since the stress amount is divided, so different grains will be subjected to a different amount of the stress. Because of that, equilibrium conditions across the grain boundary actually violated, but compatibility conditions between the grains is assured since the same amount of deformation, that means same amount of the deformation is associated with the each and every grain. So with this specified model, the response actually represents the upper bound on the average stress in the polycrystalline aggregate, and we can simply estimate that sigma c Cc into dc, that means stress in terms of the stiffness. So here this second equation actually indicates the averaging of the single behavior of the single crystal structure, and finally we can find out the sigma equal to Cc into d. So average stiffness is the average of the stiffness of the polycrystal is the average stiffness is the average of the single crystal stiffness tensor. So this is the basic philosophy to model for the to explain the Taylor model considering the displacement continuity across the layers. But this theory actually applicable generally most successful for polycrystals with the strain boundary conditions on each grain. Actually this Taylor model we have already explained to maintain the compatibility condition. So better this condition is successfully for polycrystalline, but in this case the strain boundary condition on each grain should be mentioned in this case. So this is the one model. We can explain the another model that is called SAS model, that is a lower bound theory probably in this case. And before looking into that, we can look into the right hand side figure. Here if you see that isostress conditions, so probably looking into the orientation of the fiber, in this case if we apply the compressive stress is mentioned in this figure, in that case here the stress remains the same, that is the isostress condition for all the grains, for all the components of this material, but the amount of the deformation will be shared between the two components of this material. So that means this is the total strain consists of the two components of the strain. So this concept probably we can implement to explain the SAS model. We can say that all single crystal grains with aggregate or polycrystal experience the same state of the stress. So when it is subjected to the same amount of the stress state, then definitely it will try to satisfy the equilibrium condition across the grain boundary. But compatibility conditions between the grains actually violated, the finite amount of the strain or different amount of the strain for the different polycrystals actually leads to the gap and probably or overlaps between the grains. So this response represents the lower bound on the average stress in the polycrystalline aggregate. But we can, if we find out the lower bound stiffness, here if we see from the similar strategy, we can find out that average stiffness is the inverse of the average of the single crystal compliance tensor. So this is the average tensor according to the SAS model, and it is obvious the difference between the Taylor model and SAS model only in terms of the whether we are considering the isostress deformation model or isostrain model. So this model, a SAS model, actually generally most successful for the single crystal deformation, to explain that with the stress boundary conditions on each grain. Now let us look into physically try to understand the single versus multiple shape. It will be better understood that first case, or maybe left hand side, we consider the external stress is applied. So small arrows indicate the identical stress state in each grain. So all the identical stress state in the each grain, and here each grain actually deforms according to which the single slip system is active. So that can be better explained on the Schmidt factor. So that stress by normal stress by shear stress or rate can be represented by this Schmidt factor. So that formula can be used here when the grains are subjected to the external stress, and here it is subjected to the philosophy of the single system active on the Schmidt factor. Now if we look into the external strain, that means if it is the external strain remains the same. So small arrow indicates variable stress strain, but the deformation levels remains the same. So here, if you look into this, the deformation level, that means it's a deformation remains the same for all the grains, but there is a variation of the stress state. So in this case, probably the multiple slip, which is 5 or more system in each grain satisfied the externally imposed strain. That means when you material is subjected to external strain with the variable stress state, then multiple slip system is active, and in this case it is necessary to satisfy the externally imposed strain condition, and D can be represented by this amount of the, in the elastic deformation case, the ET in terms of the, or that means modulus, elastic modulus, and the amount of the shear strain. So here we have tried to explain that the different approaches for the single crystal plasticity models, but I have not explained in terms of the details of the model. Probably there is a several, it can be extended to develop the different kind of crystal plasticity model, or to explain this phenomena what we have discussed in a crystal plasticity model. So thank you very much for your kind attention.